OK，怎样？考试拍了吗？Easy, OK OK, very hard, so hard。出什么啊？有出那个什么啊？Forces equilibrium。So hard, so hard. Okay, never mind. When you get your paper, you let me see lah. Okay, today we will enter the next chapter. Heat, heat. Okay, let me share my screen. OK，这边我看到我的 line 有点慢啊，那个声音 OK 吗？有 lag 吗？等一下我去开门先，有点我关住门会很慢。Okay, testing sound. Is the line okay? Okay, I'm going to close my camera also so that I get better connection. Okay, so I want feedback from everyone. Is it okay? I see Naomi said the line is okay. How about the rest? Can you hear me? Just to make sure that you all can hear. Yes, okay, great. Okay, thank you. Okay. Right. Okay, now first about the heat chapter. Okay, first I want to go through the difference between heat and temperature. Now, who can tell me what is the difference between heat and temperature? Just give it a thought. Simple answer. The difference between these two. Heat is energy, yes. What about temperature? Isn't temperature an energy? Sounds like they look the same, right? Heat and energy. Are they the same or are they not the same? Okay, now, these two things they are completely different things. Okay, now, how is it differ? Now, let me give you a perspective here. Let's start with temperature first. Let's start by defining, okay, defining what is temperature. Okay, temperature is the average kinetic energy of all vibrating molecules. I repeat, temperature is the average kinetic energy of all vibrating molecules. So meaning that, let's say you take one substance and then you zoom in, you observe the molecules inside. The molecules vibrate, okay, and they vibrate very fast. Now, when they vibrate, then they have kinetic energy, right? They have kinetic energy. So if you take the kinetic energy of every single molecules, you add them up, and then you divide by the number of molecules, you get the average value, right? You get the average value, and this average kinetic energy communicates the temperature of the substance. Let's say you put a thermometer in the substance, you want to measure the temperature. This vibration of the molecules, it gets communicated to the thermometer, okay? It gets communicated to the thermometer, and then the thermometer reads the temperature for you. Okay, so if I say that temperature is average, right? It means that one single molecule does not have a temperature, because one single molecule, you cannot get the average. Okay. Remember, temperature is always the macro thing. It's always a macro. We have to look at all the particles like collectively. That gives a temperature. Okay. Now, and one more thing is about the vibration of particles inside the substance. There's a range of vibration, or there's a range of kinetic energy, meaning that there are some particles that vibrate faster, and then there are some particles they vibrate much slower. Okay, they don't vibrate at the same kinetic energy. Some will move faster, some travel faster, some vibrate faster. Okay, some will be slower. So this is why some particles, the particles that can move faster, they are able to escape from the substance. Let's say you have a beaker of water. Okay, now there are millions of molecules, right? So the molecules that have enough energy that they can move faster, they can escape from the water surface, and that only happens at the surface closest to the surrounding air. Okay, so that's evaporation, right? Because you can make a liquid evaporate without boiling it. Okay, so that's how evaporation happens. Some particle gain enough energy, they can escape from the surface. Okay, now take the definition of temperature. It is the average kinetic energy, meaning that if you have a few molecules increase in kinetic energy, it's not going to affect much on the temperature. Because let's say you have 1 million molecules. If only 5 molecules increase in kinetic energy, that's not going to affect the average value, right? The average value is still the same. Okay, because the 5 molecules compared to the millions of molecules is nothing. Okay, so there has to be a overall increase in the kinetic energy, only then the substance temperature will rise. Okay, remember that one. Now, just now just now I mentioned that there are particles that can vibrate faster, and there are particles that vibrate slower, right? That all depends on the mass. Okay, one of the factors is the mass of the particle. The heavier particle, right? The heavier particle, they move slower, generally speaking, okay? And the lighter particle, they move faster. So if you see our atmosphere, right, is made of like nitrogen and oxygen and carbon dioxide and stuff, right? So let's say nitrogen and oxygen. Nitrogen is much lighter than oxygen. So if you could separate the nitrogen from the oxygen, and then you get a bunch of nitrogen here, this nitrogen, they are going to be hotter than the oxygen. Why? Because nitrogen, they are lighter molecule, they vibrate faster, right? They have more kinetic energy. So if you could separate these two gases, right, then you'll find that the nitrogen actually is warmer than the oxygen. The oxygen will be cooler. Okay, so because of the average temperature is just the average kinetic energy. When you combine these two gases together, you get only one single temperature, the average of everything. Okay, so that is for temperature. Understand that. Now we go to heat. Okay, we go to heat. So heat is when you look at one particle. Let's say you look at one molecule. And then you ask the molecule, okay, how much energy you have? Write the number down, okay? And then you go to the next particle. You ask again, how much energy do you have? Write the number down. Go to every single particle you can find in the substance. Write all down, and then you add up everything. That is the amount of heat in the substance. Okay? So heat is the total kinetic energy of every vibrating molecules. That is how much heat that the substance contains. Okay, so the difference, one is average, one is total. Now, here's the thing, you see, your cup of coffee, in the morning, your cup of coffee at a temperature of 80 degrees Celsius is hotter than the ocean, but the ocean has more heat than your cup of coffee. How is that possible? Okay, you see, back to our definition. Your cup of coffee is hotter, okay? It's hotter than the ocean because the average kinetic energy is higher. But the ocean has more heat because the ocean has more particles, is way more particles than your cup of coffee. There are trillions and trillions and trillions of particles in the ocean. If you add up every single kinetic energy of every single particle, that gives the total energy of the ocean. Okay, so we can say that a hot object, right? A hotter object does not necessarily mean that it contains more heat. I repeat, a hotter object does not necessarily mean that it contains more heat. It's two different things. Understand, huh? Okay, so that is the difference between heat and temperature. So you see, people say that climate change, right? People say that climate change could affect the global warming and the temperature of the ocean rises, all that stuff, right? And some say that the ocean, the temperature of the ocean could rise like 1 degree or maybe half a degree. And then other people, they will say, okay, 1 degree is not that much, right? Imagine the ocean just rise 1 degree, that's not much. But if you really think of it, right, rise 1 degree, that is the temperature, right? So if the temperature, which is the average kinetic energy, rises 1 degree, imagine how much total energy that it increases. Because if you want to push up the average kinetic energy by 1 degree, think of how many molecules in the ocean. If you want to push up the average value, that is equivalent to the increase, okay? Increase in kinetic energy of every single particle in the ocean. Okay, so that's why they said increase in 1 degree of the ocean. That is a tremendous increase in the total energy of the ocean. Okay, so whenever the sun, right, the sun shines like the earth, okay, it's supplying energy, right? So everything absorbs the heat energy. You have the air, so the temperature of the air rises. You have the land absorb the energy, and then you have the ocean absorb the energy. Most of the energy will go to the ocean. Yes, the ocean always wins the game. The ocean is the one that captures the most amount of heat energy. Okay, so there's huge amount of energy stored in the ocean and not being used. They are somewhere in the ocean and then they are lurking there. It's not being used yet. Okay, now later we'll come to that. Why is the ocean able to capture the most amount of energy? Later we'll go to the later sub chapters. We'll talk about that one. Okay, but in this chapter, it's just that you need to be able to differentiate very clearly the difference between these two physical quantities, okay, heat and temperature. Now, if I write down, okay, just to write down the points, okay, so heat versus temperature. Heat is, okay, energy. Heat is the energy itself. If I say I feel the heat, I don't say I feel the temperature. Doesn't make sense. Okay, I feel the heat. It is the energy that gives me the sensation. Temperature is not the energy, it is a measurement. Okay, it is a measurement. And then definition, okay, we already gone through the definition. You can talk about what's the difference between these two. But in terms of the unit, okay, heat is a derived unit and temperature is a base unit. Remember your derived and base in the very first chapter, right? So temperature is a base quantity, it's a base unit. So it can take degrees Celsius or Kelvin. Heat in joule because it is energy. Okay, yeah. So a few differences between these two. And then the last one is, of course, the definition. You can say that heat is the total kinetic energy, and this is the average kinetic energy. Okay, and there's sometimes you see in your book they have second version of definition. They said that it is a degree of hotness. That is also acceptable. Degree of hotness and coldness can be defined in this way also. So temperature is the degree of hotness and coldness. Okay, now suppose let's say I have a cup of coffee. I put it on a table. And then the surrounding air is at room temperature, let's say 26 degrees Celsius. And this is 80 degrees Celsius. Okay, now, here I observe, if I make a hot cup of coffee, I place it in the surrounding room temperature, and I observe after a few minutes, what happened to the temperature. Now, the temperature, everybody could agree, right? The temperature, of course, it would drop. Okay, the temperature of the coffee would drop. After a few minutes, you'll see that from 80 degrees Celsius, it would drop all the way to the room temperature, 26 degrees Celsius. Okay, now what is happening here? You see, temperature drops means the average kinetic energy drops, right? So meaning that there is a loss of energy. Loss of what energy? Loss of heat energy. From where to where? From the coffee and a coffee cup to the surrounding. So the energy goes to the surrounding from the coffee and the coffee cup. Okay, it goes to the surrounding air and it goes maybe the table, goes to the table here. So here there's a system and a surrounding. You see, in physics, it's always very important to differentiate between system and surrounding. What is a system here? System is the coffee and the coffee cup. Okay, the surrounding would be whatever that is closest to these two objects, which is the table that is in contact with it, and also the surrounding air. That is, we define it as the surrounding. Okay, so there's an escape of heat from the system to the surrounding. That's why the temperature drops to 26. Okay, focus on the flow. What is going out here? This is the heat, right? The heat flow. The heat flow. It flows from where to where? From hot to cold. The surrounding air is cooler. The coffee and a coffee cup is warmer or it's hotter, okay? So heat always flow from hot to cold. Remember that, okay? Heat always flow from hot to cold. Now, suppose another case, I put a glass of cold water, okay? I put a glass of cold water, some ice cubes, and it's at 5 degrees Celsius. And surrounding air is warmer, again at room temperature 26 degrees Celsius. So we have temperature difference again, right? What happened after a few minutes? You can already guess. The cold water will increase in temperature and it will become warm, right? So from 5 degrees Celsius, it will go up to the room temperature 26 degrees Celsius. Okay, then we see what is happening here. How come the temperature will go up? Does it mean that the cold is escaping from the water? Can we say that? Because you see, for the coffee, heat is escaping from the coffee. That's why the temperature drops. If this one, temperature rise, does it mean that the cold is escaping from the glass of water? No, we cannot say that, because there is no such thing as cold. Okay? Cold is just an absence of heat. There is no such thing as cold, remember. So we cannot say that the cold has been transferred. Okay? So we say that the heat from the surrounding, which is the warm air and the table, that is my surrounding. Heat from the surrounding has been transferred to the system. Okay? That's why there is an increase in the average kinetic energy. Again, look at how the heat flow. In these two examples, I can say that what is flowing? What is flowing? Heat is flowing. Heat is flowing, and it's flowing from where to where? It's always flowing from the hot region to a cooler region. In the case of the ice water, the heat flows from hot, which is the warmer air, okay, the warm air, to the cold water. In the coffee, the heat flows from the hot coffee to the cold air. It is always from hot region to cold region. It's never the other way around, no. Okay, and also we know that there is no such thing as cold. No such thing as cold. But then what is cold? Cold is just an absence of heat. Okay, you see, I can take the heat energy, I can add it to a substance. I can keep adding the heat energy, keep piling it on. Okay, keep adding, and then the substance become hotter and hotter. If I want to cool it, I cannot add the cold. I remove the heat. Okay, I remove the heat from the substance. I keep on removing. So that process of removing the heat is actually cooling. Okay, so cooling is just right here. Cooling is just a removal of heat energy. Real life example, like your aircon. Okay, you see, your aircon keeps the room cold, right? If you're in a room, you feel cold. If you're outside of your room, then you feel very hot because of the aircon fan, the radiator, right? So how it works is that the aircon, it pulls the heat from your room. There's heat in your room, right? There's heat from the everything, okay? Every object is constantly giving out heat at a certain degree. Even human body still giving out heat, okay? So the aircon pulls the heat from the room and then it throws it outside. Okay, so this is why every time you go to the back of your house at the aircon radiator, you feel very hot there. Okay, but inside your room is very cold because all your aircon does is just to keep pulling the heat from the room and throw it outside in the surrounding. Pull again and then throw it outside. It's eliminating the heat from your house. Okay, and dissipate it into the surrounding. Okay, into the surrounding. And then the interesting thing is that the aircon can do the opposite. The aircon can reverse the process. It reverses the process, and then it can pull the heat from outside and add into your room, your house. That is a heater, right? But we don't really use that here, right? Malaysia is very hot. So in the winter season, outside, overseas, in the winter season, okay, they have heater, right? They pull the heat from the cool air outside and then keep the house inside warm. Now, maybe you wonder why, how come you can pull the heat from outside? Because outside is very cold, right? During the winter. Okay, during the winter season, outside is very cool. How come there's heat there? Okay, now understand that even cool air has heat. Unless the substance or the air reaches absolute zero. Everything has heat, everything has certain degree amount of heat unless it is at absolute zero. What is absolute zero? Absolute zero, guys, absolute zero is the lowest temperature in the universe, or lowest temperature achievable. Okay, no, we cannot say achievable because we have not achieved it. Okay, it's the lowest temperature discovered in the universe. Okay, that equals to negative 273 degrees Celsius. Okay, that equals to negative 273 degrees Celsius, or we can say that in other measurement, it is called 0K, means Kelvin. 0 Kelvin. Later, I'll talk about this one, okay? The Kelvin to convert to degrees Celsius, okay? But absolute zero is negative 273 degrees Celsius. So when an object is not at its absolute zero, it always contains certain amount of heat. So even if it's cold air outside, there is still heat inside the air. You can still get the heat from cold air. If the object reaches absolute zero, then there will be no more heat in the object. Okay, so now, if you think about heat is just kinetic energy, right? Is the total kinetic energy. So what does it mean if a substance is at its absolute zero? If a substance reaches the absolute zero, it means that the substance will have no kinetic energy because it's the coolest, and in the absence, completely absence of heat, there's no more energy. So the substance will not be moving. Okay? So when a substance reaches absolute zero, it will not move. It will stay completely still, not moving. Is that possible? That's not possible. Okay? In our current world of understanding, this is not possible. Meaning that it is not possible for an atom to like stop completely, like not moving at all. It is not possible due to our current understanding of the science. Okay, this is why we cannot achieve absolute zero. You cannot cool a substance down to absolute zero. You can only cool it down to very, very close to absolute zero. In fact, the scientists, right, you see, the scientists in the lab, they managed to cool the object down to negative 273.15. I think it's around this number, if I'm not mistaken. They managed to cool the substance down to this temperature, but it's not absolute zero yet. There's still a difference here, right? Okay, so meaning that at this temperature, the atoms still move. It still have kinetic energy, a small amount of kinetic energy. Only when it reaches negative 273, it has zero kinetic energy. Okay, so we cannot achieve the absolute zero. Even until now, we cannot achieve it. We can only cool it as close as absolute zero. And if you manage to cool object down to this temperature, that object will behave very strangely. The object will behave very strange. How strange? You get like, you've heard about like things like super conductivity or superfluid. What is superfluid? Superfluid is like, you see, there's an experiment, right? They put the water in a cup and then they cool the water down to very, very cold. I forgot what is the temperature already. It's just very, very cold. It's cold until very close to absolute zero. And then this fluid, right, it behaves as a superfluid. It's like the fluid, right, it can climb through the walls of the cup and spill by itself. Spill by itself. Meaning that you don't need to move the cup. You just hold it like this. And then the water, suddenly it can climb through the walls, the walls of the cup. It can climb and then it can spill itself. Okay, that is one characteristic that the substance can show when it is at very, very cold temperature. So a lot of strange things will happen when you cool it down to absolute zero. Okay, that is called a superfluid. And also superconductivity is where you have like very, very low resistance. Okay, very, very low resistance, all the electrical current, okay, without high resistance. Okay, so it's just that material behaves in unique ways, okay, when it is being cooled to a very low temperature. Okay, let's come back. Now. Come back to the absolute zero. So absolute zero is, I said that is 0 Kelvin, right? We got two temperature scale. So Kelvin, 0 Kelvin is equals to negative 273 degrees Celsius. So whenever you want to convert from Kelvin to degrees Celsius, you minus 273. And whenever you want to convert from degrees Celsius to Kelvin, you add 273. For example, 23 degrees Celsius. What is it in Kelvin? I would add it plus 273, and that would be 273, 23, 296, 296 Kelvin. OK， 当你要换 degree Celsius 去 Kelvin， 你加273 fix 了的这个 number。同样的调转你就减273，所以0 Kelvin 你加273 ，sorry， 你减273就是减273 degree Celsius。OK， 我们有2个 scale 通常你会用到的，在我们的 heat chapter will be Kelvin. But both are actually both you need. Okay. Okay, now I want to check the connection again. It keeps showing the lagging. It's very annoying. Give me some feedback if you still, until here, if the sound is still okay.
It's okay, teacher.
Okay, all right. Thank you. Right. Sometimes only. Okay. Yeah, because it keeps showing the internet connection is unstable. That is very, very annoying. Things is okay. Never mind. I have it recorded down just in case if you miss something, you can go back and you can see it. Now let's continue. Okay. Let me erase this. Next is we look at, okay, let's say, so far we talk about cooling and heating, right? Heating is I add the heat energy, cooling is I remove the heat energy, okay? Now suppose that we have a hot metal cup filled with hot water, say it's 70 degrees Celsius. And then I put the metal cup inside a styrofoam cup filled with cold water. The cold water is at 5 degrees Celsius. Okay, I put the metal cup filled with hot water inside a styrofoam cup filled with cold water. What will happen after a few minutes? Give it a thought. Okay, what will happen after a few minutes? What final temperature will they reach, both in the hot water and in the cold water? Okay, guys, left 1 minute. So I'm going to create a new meeting and we'll continue from there.